So we'll discuss about the transmission gate. So we know that the MOSFET, whenever we turn on, like for example, let's consider these, uh, let's consider this NMOS. I'm drawing it in this direction so that for some particular region, which will be clear eventually. So this is my NMOS, right? This is my gate. So this is my gate and this is my drain and the source. So we know that the NMOS, whenever we apply a very high potential, let's the highest potential in an IC, maybe let it be VDD. So whenever we give this gate voltage as VDD, we know that the MOSFET, there is a channel is formed and the impedance formed is very low. So this can be used as a switch, and we'll see that we can implement different logics and different things we can use. And switch is a very important aspect in any circuit design, whether it may be digital or it may be analog. Switch is as an important, very important aspect like that. So this transistor can be used as a switch. So that's why it's called a transmission gate, and we'll see how combination of NMOS and PMOS leads to a very good transmission gate in today's class. So let's start trying to analyze that how this acts as a transmission gate. So we know that whenever we apply a voltage which is, let this VG, the gate voltage, is equal to VDD. So then this channel is formed, and whenever this is 0, we know that the channel it is in cutoff region and the switch is off. So the switch is off whenever this is VG is 0, and whenever this VG is equal to VDD, the switch is on. So what I can get is, if I apply some input here, definitely I'll get some output here, V out. So of course this out will have some it will be driving some other circuit. So let's represent it by a simple capacitor, right? Which is again a parasitic capacitor, CL. So it will be definitely driving this load. So if I apply some voltage V in, so because this gate is turned on, so this is all this is, you can say that, so this is turned on, and because of this on, whatever the voltage that we apply here, so eventually that voltage will come here. So that's why this can be used as a switch. So it's a transmission gate basically. Now we have to understand here, like what happens, like does any voltage that I apply here, eventually this voltage will become the same as V in, right? Is V out equal to V in? Suppose if I give some time for this capacitor to charge and some time, then will this V out be equal to V in? So that's my question. So will V in equal to V out always, right? As suppose like I'm t goes to infinity, so I'm giving a sufficient amount of time, so I have applied a V in and I have given a sufficient time t equal to infinity, then will V out be equal to V in? But this is not true always. So let's see what happens. Like, so let's imagine that I have applied a logic 1, like that. Let input logic 1, or you can say that if you consider the logic 1 as VDD, suppose. So I have applied an input logic 1, right? This V in is equal to VDD. What happens to, so this is the condition, I have applied a VDD here, VDD here. So so my question is, what will be this V out, right? So of course, because this VDD is applied here, VDD is applied. So initially, let's assume that initially at V out at t equal to 0, the output is 0, right? So initially this output was at 0 volt, right? So what happens to these capacitors? So CL, will it charge? Will this current will flow here, and will it charge till VDD, right? Will it charge VDD? So that's my question. So So in this situation, what happens is, yes, so initially the voltage was at very low, so zero, right? Initially zero, and a current will flow through it. A current will flow through this capacitor, and it will try to charge. It will try to charge this capacitor. So it will try to charge this capacitor, but it will not go till VDD, because what happens is, as this voltage goes up, as this voltage rise up, right, initially it will be in saturation region, because I can consider this as a source and this as a drain, and because the gate and the drain are at same potential, the MOSFET is in saturation region. But what happens is the voltage will rise up, and a time will come when this voltage will be VDD minus VTH, or the threshold voltage of the inverter. So a time will come when it will rise from 0 to VDD minus VTN, which is the threshold voltage of this MOSFET. So after this, if this voltage becomes higher than VDD minus VTN, basically the VGS drop, you see, VGS drop cannot be, cannot be less than VTN. If the VDS drop becomes, if the VGS drop becomes less than VTN, then the MOSFET will be in cutoff region, and this will be in off state. So this will be on off state, and there will be no current flowing. So the maximum voltage this V out can reach is only VDD minus VTN, because after this voltage, if it tries to increase, this MOSFET will go into the cutoff region. So in this situation, V out max is VDD minus VTN. Now, what happens when I am applying a logic 0? So, again, we'll try to analyze the same situation. So, the next situation is input is logic 0. So in this case, I have applied a logic 0, right? Logic 0 means V in is equal to 0 volt, and V out initially, let's assume it to be at high. So basically we are trying to analyze, let it consider to be at V out is something at VDD. Of course, maximum it can reach to VDD minus VTH minus VTN. So now if I apply a logic, suppose it is at VDD, it is at this is at zero potential, and initially it was at VDD, right? Initially it was at VDD. Now definitely, because of this zero potential, a current will be flowing in the reverse direction, right? Because from this high potential to the lower potential, and this is on. So and eventually it will discharge from VDD to it will go till 0. So it can go till 0, because what happens is, if it goes till 0, we have a good amount of VGS drop. So VGS drop actually because this potential is higher, so in this case actually this happens to be the drain and this happens to be the source according to the convention. So because whichever is at higher potential, it is termed as gate. So in this case, this happens to be the source, because this will be at higher potential, this is already at zero potential. So and current is flowing in this direction. So we know that the drain, and in an NMOS it goes from drain to source. So initially it goes to VDD, and because the VGS is very high here, VGS is equal to VDD here, so definitely it is on in all the conditions. So that's why it easily goes from VDD to 0. So the minimum voltage in this situation is minimum it can go here is um, 0 volt, right? 0 volt. Okay. So in this case, so what we understood here is, yeah, there is a limitation, like na. The maximum voltage in this situation, it can go only the VDD minus VT and the threshold voltage. However, the minimum voltage, it can go till minimum voltage. So this, because the VDD has, because the logic high has not gone till VDD, that's why there is a loss of, you can say that, one threshold. So this is termed as, or this is also called as threshold voltage loss. Right, this is also called as threshold voltage loss, because we are losing one threshold at the, whenever it is trying to transmit logic high. So similarly, if I use a PMOS device, so the opposite happens, can someone tell what will happen in case of PMOS? So if I have a PMOS, suppose if I have a PMOS here, so get again V in, V out. So what will be my V out if my V in is equal to 0 volt? What will be my V out? And if my V in is equal to VDD, what will be my V out? So in this case, I have assumed the gate VG is given as 0 volt, right? Because to turn on a PMOS device, we need require the the gate voltage to be at 0 volt. So can someone tell me? Yeah, can someone tell me what is the? You can tell your name and you can tell me the voltage. What will be like that in case of PMOS? When it is 0, what will be V out?
Mod VTOP.
Yes?
It will be mod VTP, sir.
Okay, in case
Yeah.
when it is V in, and
V equals.
okay, and when it is V in equal to VDD?
V out will be VDD.
Here will be VDD. Okay. What is your name? Sorry, I cannot see whoever is speaking.
I'm Raviteja, sir.
Raviteja. Okay, thank you, Raviteja. Yeah. So similar things will happen in case of the PMOS. So what happens is, when V in equal to 0 volt, right? Because again the same situation will happen like in case of the NMOS. We need a minimum, because this is at 0 volt, so we need this whenever it is 0 volt, and this will be, suppose initially it is initially suppose it is VDD, so there will be a minimum threshold drop between the gate and the, gate and the source. That's why, we can say that this V out will only go till VT there. So there will be a threshold, one threshold voltage drop. So it is in case of whenever it is V in is 0 volt. However, whenever this V in is equal to VDD, right? V in is equal to VDD, then what happens is, because we have a good amount of VGS, right? Good amount of VGS, that's why this V out will go to VDD. So in this case, the VGS will be equal to VDD, because we know that for a PMOS, the reverse separation happen, right? whenever these voltages are high and this is low, there's a potential difference, so there will be a VGS. So that's why the V out will go to VDD. So from this we can conclude that the PMOS device has a problem whenever the Vin is equal to 0 volt, but it can easily transmit Vin equal to VDD, right? Whereas in case of NMOS we have seen the reverse. The NMOS can easily transmit whenever the logic is 0, it can easily transmit here, uh, but it cannot easily transmit when V in equal to VDD. So these two has two different problems. So the final conclusion is NMOS can I should say easily, no, without any loss, easily transmit, I should say, 0 volt, and whereas the PMOS can easily transmit VDD. So both of them have their own drawbacks. Both of them have their own drawbacks. So the what we can do is, we can combine these two. We can combine them, and it leads to a kind of CMOS transmission gate, right? CMOS transmission gate, where we are trying to take the advantage of the both, because because in a signal, the signal will go from 0 to VDD in case of a digital signal. So we have to transmit both 0 volt whenever the Vin is 0, and whenever the Vin is VDD, we need to transmit both. So that's why we need the combination of both. So that's why we need the combination of both. So if we try to combine this two, this one, then will lead to transmission gate like that. So just before proceeding, I'll just ask one simple more question, so anyone of you can answer. So this is again one more problem. So if we try to combine multiple circuits, especially with NMOS, suppose if I am applying here, and so so this is at VDD, right? And this is also at VDD. This is at VDD, right? So can you tell me what will be the voltage here? Can anyone tell me what will be the voltage here?
VVD minus 2 VTH.
Okay. Again, who is speaking?
Madhav sir.
Madhav. Okay. Yeah, definitely. Thank you. Sorry, actually, I cannot see who is speaking. That's why I have to ask the name, and it's difficult to identify the voice. So thank you. Yeah, definitely. This is VDD minus 2 VTN, right? So because here the drop, it can go up to maximum VDD minus VTN. So again, there will be one more drop like that. So this is the problem with this kind of, when we are trying to implement this switch only with a single MOS. So, and that's why it is that's why it is the main motivation, like especially if we are combining this multiple transistor to form a logic. That's why, like, as we combine more transistor, you see we are losing in one combination we are losing one threshold. So if the threshold voltage maybe 300 millivolt like that, then after this we are losing a voltage of around 600 millivolt, and if VDD is like around 1.2 or 1.5, so we are losing a lot of like that. The noise margin is getting affected in the upper half, because the VOH, here you can see here VOH is this is the VOH, right? The maximum output, highest voltage of the output. So you can see that the output is reduced by 2 times threshold voltage. So that's why your noise margin is getting affected. So that's why, as I mentioned, so we will be combining this NMOS and PMOS so that we can get a transmission gate like that. So this comes out to be the CMOS transmission gate, right? So I think everyone can mute, please. Yeah. So for drawing the transmission gate, I'll be using a little different notation of the NMOS and PMOS because the arrows get confused. So generally, and secondly, it is very tricky because for an NMOS, whichever is at higher potential, we term it as a drain, and whichever it is, because both are symmetric, right? So whichever is at higher potential will term it as a drain, and whichever it is at lower potential will term it as a source. That's why it's this arrow marks will keep changing, either here or here, like that. So to get this confusion, so we'll use different notation like that. The NMOS is represented by this one, right? The NMOS is represented by this, and the PMOS will be represented by this bubble, right? So this is different way of I think we have discussed in the previous class. So this one notation of the PMOS, this one notation of the NMOS. So the transmission gate, as I mentioned, is nothing but the combination of these PMOS and NMOS. So I can have a PMOS here. I can have an NMOS here. So my PMOS is here. This is here. So this is my V in. Again, of course, this is V out. Of course, there will be a capacitance. This is a parasitic capacitance. Again, which comes from the gate of the next stage, and also the capacitance from is on these devices. So CL. Now the voltage that I will apply here is of course if I apply a voltage C here, like control voltage, maybe controlling this one, I need to apply a bar opposite, right? So if I want to turn it on, right, turn it on, if I should turn on the NMOS, we know by giving the gate voltage as VDD, and if I want to turn more the PMOS, I should give a bar or 0 volt, right? So because I want to turn both of them on together, so if I am applying a VDD here, I should be applying 0 volt here, right? So I should be applying a 0 volt here, and I should be applying a VDD here. And if I want to turn off, I just apply a 0 volt here, and I'll be applying VDD here. So then PMOS and NMOS will be turned off. So this is the how the CMOS transmission gate work. So of course the current flowing through it is the summation of the current flowing through the PMOS and NMOS. So if I call the current flowing through the NMOS as IDP, and the current flowing through the NMOS as IDN, so the current total current ID, let's call it as ID total, is equal to IDN plus IDP. So that's the summation of these two current, like that. So let's now try to understand, now try to understand how does the operating region of this NMOS and PMOS changes. So let's consider the situation whenever suppose this logic is this V out is a 0 volt and this V in is equal to VDD. So and of course here applying this to turn on, I am applying VDD, and this will be 0. So let's try to understand this special condition. How does the region of operation varies, like that? So let's delete different one. So in this situation, what I have applied is I have applied a VDD because I want to turn this on, and then I have applied a 0 volt here, and my V in is equal to VDD again, and then this V out, we want to see that V out is, as this V out varies, how does this two MOSFET operating region varies like that. So and V out is going from 0 volt, right? V out is starting from 0 volt, it is increasing, right? So let's try to draw this x-axis. So here in the x-axis I am trying to draw V out, and I'll try to see at different regions of operations how does this is changing, right? So let's start with let's start, I have here at you know it starts with 0, and at whenever this is at VTP, right, threshold voltage of VDD, there will be some changes, and whenever it reaches VDD minus VTN, which is the threshold voltage of this NMOS, this is VTP, is the mode of the threshold voltage of the PMOS, and till VDD, right? So we'll try to slowly go one by one and try to understand how does the operating region of uh, NMOS and PMOS varies. So of course this will be different whenever we take V in is as 0 volt, right? Whenever we take V in as 0 volt, then this variation, this curve will vary like that, right? So let's try to understand. So whenever this is at 0 volt, or this is at 0 volt, right? So we can see here, right, in for the NMOS, this is at zero potential and these two are at same potential, right? So this is at lower potential or zero potential, so because of which I can turn this as a source for in case of the NMOS, and it is like as if the drain and the gate are shorted and connected to VDD. So in this situation it is something like this. So my drain and source are connected to VDD for the NMOS, and this is connected to the ground. So in this situation the NMOS is in saturation region. So NMOS will be in NMOS will be in saturation region. Now, if I slowly, if I slowly, because as this V out, so these two are already connected, this VDD and this will be always be connected to VDD. Now, slowly I am increasing this, slowly I am increasing this voltage. So, and of course, even if it cross this point, so I am slowly increasing this voltage, and it will in this region also it will still be in saturation region, right? It will still be in saturation region because even if this voltage has increased to BTP, the VGS is VDD minus BTP, so still it will be in saturation region. Now as soon as this voltage after increasing, it reaches VDD minus BTN, right? So as soon as it reaches, and if it becomes crosses this one, so this one it crosses this one, definitely this transistor will go in cutoff region, this NMOS will go in cutoff region, because my VGS here in this case will be less than VTN. So NMOS will be cutoff region in this state. So NMOS will be in cutoff region whenever this voltage will be crossing VDD minus VTN. So this is the situation. So whenever the Vin is equal to VDD, so my NMOS is in saturation region from 0 to VDP, and NMOS is again in saturation region whenever it's from in again if the voltage is above VTP, but if it is less than VDD minus VTN. But as soon as it becomes more than VDD minus VTN, because my VGS will be less than VTN here, then it is in cutoff region. So this is the situation for the for the NMOS. Is it clear? Any question like that? Any question on this? Is it clear? Everyone is following, or it's complicated or not able to follow? Please comment. Yeah. Any comment?
No doubt, sir. It's clear.
Clear. Other students? Yeah, mother. Thank you.
Yes, sir. Clear.
Yes, sir. Clear. Clear, right? Great. Good. So, so now in case of the PMOS, so let's try to understand. So again, this is connected to 0 volt, right? Gate is connected to 0 volt, and one of the node is connected to VDD, right? So it's like as if its drain voltage is changing. This is, we can term it as source, and this is the gate, and this is the drain, right? Because we know that the source is always at higher potential in case of the PMOS. So now if we see this drain voltage, so initially it was at 0 volt, right? 0 volt. So initially it was at 0 volt, and we know that when these are both when drain and two drains are at 0 volt, so in this situation, so this PMOS will be in saturation region. So this PMOS is in saturation region here also whenever it's close to 0 volt. Now it has slowly started rising, and it has become more than the threshold voltage, right? It will reach till threshold voltage, and we will go in this region, it will become more than the threshold voltage. So as soon as it will reach this threshold voltage VTP, right? As soon as it reaches this threshold voltage, magnitude of the threshold voltage, and it becomes higher, we know that whenever this potential becomes higher than the gate voltage by the threshold voltage in case of the PMOS, we know that the PMOS goes to the linear region. Of course, you see here that gate and source are always constant. The VGS is VDD. So this drain has become BTP, and if as it goes higher than BTP, the PMOS will go in the linear region. So in this region, when V out is going higher than, so this is the V out node, right? So whenever this is going higher than BTP, it goes to the linear region. So similarly, as it keep increasing, right? As it keep increasing, the VDS becomes smaller and smaller, and even if this crosses, because the VGS is always high VDD, so PMOS will be in again in linear region, in this region also. So we can see that the PMOS is in saturation region here, and it is in linear region, and it is in linear region. Sorry, excuse me. So you can see here that this in this case the NMOS is in saturation region, but it has gone to cutoff. But because the PMOS is on, it is in linear region. That's why the whole it's still conducting, right? So we can see that in all the regions from 0 to VDD, we can see that we can see that this transmission gate is always on, right? This transmission gate is always on. Like that. Any questions till this point?
No, sir.
No, right? So yeah, I hope everyone is following. So if there's no question, then either yeah, all of you are understanding it, or or I'm not able to explain properly. So anyways, so so your feedback is important. If you are understanding it, everything, it's great. So now next is, how do we analyze this, like that, what is the equivalent resistance, or I can say that, of course, the because this MOS is changing in different regions, so definitely, if I definitely this is a non-linear device, the resistance is not constant. Like I can approximate within resistance, but this resistance is definitely not be constant, um, because this all these MOSFETs are going from different region, but we can do some approximation. We can do some approximation. So if I try to find out the equivalent resistance, then how it happens like that. So let's try to find out. I should copy this again, this figure. Let me copy the previous people. Okay. So now, how do I find out the equivalent resistance? So to know the resistance of any circuit, right? It can be linear or non-linear device. So, but we know that mm, we can, if I just try to divide the potential difference with the current flowing through it, then I can find the approximate resistance. So I can say that R equivalent due to this NMOS, the resistance due to the NMOS, is nothing but the potential difference between the drain and the source, and the current flowing through the NMOS. So the current flowing through the NMOS is, I can say that IDN, it's IDN, and the potential difference, we know that it is, suppose consider that I am applying a potential VDD, right? Or let's try to generalize it. So the generalization will be V in minus V out, right? So whether so that's the current flowing through. This is the potential difference between this input and the output, and the current flowing through it. So similarly, the R equivalent P will be nothing but, again, V in minus V out, and I D P. So this is the potential difference, and we can easily find out that R equivalent total is nothing but R equivalent N parallel R equivalent P, right? So now again, using this situation, let's come back and try to come back to this region, right? We know that these are three different regions, right? These are three different regions, and let's try to understand the what is this R equivalent total, right? R equivalent total in these three regions, right? So let's call these three different regions different names. Let's use different color. So let's call it as region 1. Let's call it as region 2 and region 3. So again, uh, let me copy this one so that I don't have to come up and down again and again, right? let's go to next page. Yeah. So whenever we are in region 1, right? In region 1, region 1, what we have seen? We have seen that the NMOS is in saturation region and the PMOS is in saturation region. So I can just, to find my current, total current, right? I can just simply write the equation, Anna. I can simply write this equation for IDN and IDP in saturation region of operation. So my IDN will be nothing but the, in this case, the again v in my v if, so the potential difference, right, the potential difference here is v in minus v out. So since the v in is equal to vdd, so I can write this as vdd minus v out, and the I flowing through in the saturation region, we know, in the, it is kn by 2, right, the vgs. So in this case, the because this is, region 1 is very close to, here it is 0, so we know that, right, we know that this is the vgs again, so it's close to, of course, 0. So what is vgs? Vgs is nothing but vdd minus v out, and of course the threshold voltage, right? So this vdd minus v out and square we have. So again, considering this lambda is equal to 0, and this is the vgs, right? This is the VGS, right? So this is the equation of the N, the current flowing through the NMOS in region 1. So similarly, because the PMOS is also in saturation region, so I can write as IDP equal to, again, the potential difference between these two, VDD minus Vn minus V out, is because the Vn is, Vn is VDD. So what I can write here is again Kp by 2. So in this case, in the case of this NMOS, you see the VGS here. You see this is close to, again, this is close to 0 volt, right? And this is VDD, right? So in this case, the VGS happens to be this one, right? As we have discussed earlier. So this happens to be VGS, and this happens to be the drain, right? In case of the PMOS. So that's why my VGS happens to be VDD. So VDD minus VTP. So this is my, this is my VGS. So I can say that this is my VGS or VSG, whatever. Like in case of mod, I should say mod VGS. So in case of the PMOS. Is this clear? Yeah. Is this clear? Okay, I hope it's clear. So let's go to the region 2. I'm extending a little bit because I started the class a little late. I hope you don't have class now. So region 2, I'll just finish it in next 5 minutes. So in the region 2, we know that in the region 2, the NMOS is in saturation region. So again, I'll have the same equation here in case of region 2. And of course, the PMOS is in linear region. So I just need to write the linear region equation for the PMOS. So in region 2, so I'll have the same equation for the this one, say for same equation applies for the NMOS in the region 2. So I just need to copy paste it here. And in case of the PMOS, I will require to write the linear region equation. So if I just write the linear region equation, IDP which is nothing but, we know that VDD minus Vout is common here, and it is Kp. We know that the linear region equation for the PMOS, what is that? It is basically VGS minus VTH, or again taking mode of everything, VDS minus VDS whole square, right? This is the this is the general equation for the for the PMOS. So if I substitute the value of VGS and VDS, so this is VDD minus Vout. Of course, the 2 comes up here, and this is Kp, right? I think I made a mistake here. So again, these 2 terms will come inside. A 2 term will come inside here. So which is nothing but 2 minus, so VSG. So in this case, the VSG, because again, as I've mentioned, this will be the drain and this will be the source for the PMOS. So because the VGS here is VDD, right? VGS is VDD here. So I can write it as VGS or VSG is VDD minus again this VTP, right? So now VDS, so VDS, mod of VDS is basically, in this case, VDS is again V in minus V out, or VDD minus V out, so that is the VDS. So it happens to be VDD minus V out. Again, I have this VDS square, which is nothing but VDD minus V out square. Right? So now in this case, what I can do is this VDD minus V out, I can take common, and this can be simplified to VDD minus V out. Sorry, this can be simplified, and this term can be cancelled. So finally what I'll remain here is I'll get 2 only, because I can easily cancel with this VDD minus V out, this here and here. So what I'll get is Kp into 2 VDD minus VTP here, right? And again minus VDD minus V out. So this is in case of region 2. So again in region 3, again the same equation will repeat for PMOS, and NMOS will be in cutoff region, so no current will be flowing through NMOS. So in case of region 3, IDN will become 0 because it is cutoff region, and IDP will be same as this one. So it will just be a repetition of this one, because it's in linear region, right? So it's the same this one. Is this explanation clear? Hello? Is it clear? So any questions still here? Any questions?
Sir,
Yeah.
excuse me, sir.
Yes.
Sir, region 1, region 2, the LHS is resistance or current?
Uh-huh.
Same question. LHS, I mean, left hand side is the resistance or the current? I think
Oh,
it's
sorry, sorry,
resistance.
sorry. I messed up with it. Yeah. So everywhere, yeah. It's the resistance, right? Thank you for us correcting this one. Yeah. So yeah, good question. Sorry. So basically, this V out by V in, right? Sorry. The voltage difference, the potential difference by the current, right? So yeah, this is the resistance. Thank you for catching this one. Yeah, who asked this one? Hello, can you tell your name, please?
Sir, I'm Ravitesh.
Ravitija. Okay, okay. Thank you, Ravitija. Yeah. Sorry, it's difficult to identify the person with voice. Everyone's voice sounds similar. And someone was also speaking, right? Who was he?
Sir, I had the same question.
Yeah, 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 yeah. So, what's your name?
Sahil.
Okay, Sahil. Okay, thank you.
Sir, here it's IDN only.
Uh-huh.
Region 3. Region 3, it's IDN
Yeah,
is
yeah, yeah.
zero
So,
and
I
R is infinity.
infinity. Yeah, that's right. IDN. Yeah. I'm just correcting it. Yeah. Okay. So these are all the equivalent resistance. So next time what we'll do, we'll try to plot these resistance in the next class. I think that I don't want to extend too much. So next time what we'll plot these three curves, basically the this curve and this one, and also the equivalent. So what we will be seeing that the combination of these equivalent resistance due to the NMOS and PMOS, we will see that the curve is almost constant. So if we see individually, you'll see that there is a lot of variation in the impedance. But whereas if you see collectively, the parallel resistance, it's not constant, but it seems to be constant with the voltage, right? So in all this region, it seems to be little flat. Whereas if we see the individually, the resistance happens to be varying very rapidly with change in P out. So because of this property, that combination of the NMOS and PMOS leads to a quite constant resistance. That's why this transmission gate is quite widely used in the VLSI design, like that. So this part, this discussion, I think time is up now. So we'll consider in the next class. So as I mentioned, I'll try to give assignment. I think I should have covered more. I'll try to cover a little more before giving assignment so that I can give assignment on this part also like that. So let's not. I was thinking I'll be able to cover everything today, but it seems I'm not able to cover. So after covering, then only I'll give the assignment. Okay. So okay, yeah, I'm done. Thank you. Thank you.